Alright, welcome to this video about limits and absolute value. The purpose of this video is to learn a technique for computing limits of functions, but for certain kinds of functions. These functions whose formula have an absolute value that appears somewhere inside that formula. But in order to understand this video, there's one thing you have to do first. There's a really short video that you have to watch called Absolute Values of Negative Numbers. In the YouTube thing, if I can figure out how to do it, I'll post a link to this thing. So you should be able to just click on this thing right here when you watch the video, when you watch this video. Hopefully I can figure that out. And actually in that video there are these two facts. This fact is useful for certain limit computations, but we won't focus on that one. We're actually going to use this fact. Okay, it says if x is a negative number, then the absolute value of x is equal to negative x. And if this does not make sense, you really need to go to watch this video, because that was really the point of this video. All right, so we'll use this fact at the very end of the slides. And all we're going to do in this video is actually compute this. So evaluate the following limit. Limit as x goes to 3 of this function, 7 plus absolute value of the quantity x minus 3, all over 7 plus x. And to actually solve this, what we're going to do is separately examine the right and left side limits. And in general, for these kinds of problems, it's actually, whenever you see an absolute value, limit of an absolute value, and there's maybe some other stuff, in general, it is helpful to look at each of the two one-sided limits separately. So let's do that. For this particular problem, it'll be easier to focus on the right side limit first. So here it is. This is just the original limit problem from the previous slide, but just with a plus sign there. And here's how we'll do this. Since we're only considering x going close to 3, but we're only looking at x values which are to the right of 3. We're only looking at x values which are bigger than 3. And since x is bigger than 3, well then x minus 3 is always a positive number. I mean, just think about this, right? So you could pick x as 4, and 4 minus 3 is positive 1. You could even pick, x to be very close to 3, but if it's bigger, if it's like 3.001, then 3.001 minus 3, well that's 0.001, but the point is that you do get a positive number out. And since x minus 3 is positive, the absolute value of x minus 3 is just the same thing as x minus 3. Okay, so then to compute this limit, here's what you're going to do. All you do is replace this absolute value x minus 3. Since we know based on the type of x values we're considering, this is just the same thing as x minus 3. So absolute value of x minus 3 was just replaced with x minus 3. So this limit should just be the same thing as this limit. And this limit you can just compute using the direct substitution property. You actually have polynomial divided by polynomial. So this is a rational function. And you can plug in 3 into the denominator, so 3 is actually in the domain, and just using good old direct substitution property for rational functions, you get that the limit on the right is going to be 7 over 10. Now what about the left side? So let's look at the same function again. Original function with the absolute value, but now approaching 3 from the left. Since x approaches 3 from the left, we're only considering when x is smaller than 3, and if x is a number that's smaller than 3, then you have x minus 3 is negative, right? Because you have a number smaller than 3, and you subtract this bigger thing, 3, so you're looking at a negative number. And the point is this: replace absolute value of x minus 3 with negative the quantity x minus 3. And this is really the whole point of that previous video that I want you to watch. To explain this in just a little bit more detail, the fact which was quoted earlier, only with x's, here it's been replaced with z's. Here's the fact restated. It says if z is a negative number, then absolute value of z is equal to negative z. So it's this fact that we're going to use, and if you want just to really take this in steps, we're going to take this fact here and just restate this fact. We'll just rewrite this thing, but plug in for each z 1, 2, 3 spots where z occurs. Just replace z with x minus 3. So let's do that, right? Rewrite this if, and then replace the z with x minus 3, and so on. So this sentence here should read like this: if x minus 3 is less than 0, then the absolute value of x minus 3 is equal to negative x minus 3, right? And we do have that x minus 3 is less than 0, right? That's what we established right here. X minus 3 is negative. So since we've met this requirement right here, then we can now use this fact, right? So that's why I want to replace absolute value of x minus 3 with negative quantity x minus 3, because this thing is equal to this thing, and we can replace this thing with that thing. So we'll rewrite this limit here, but absolute value of x minus 3 is now going to turn into the quantity negative quantity x minus 3. So we'll just do that, right? So absolute value turned into parentheses, but this plus had to turn into minus because of that minus sign right there. Then to compute this limit right here, we just use the direct substitution properties before, because 3 is in the domain of this rational function. Can plug in 3 and get 7/10. So look, the limit on the right and the limit on the left were both equal to 7/10, but it was easy to analyze these as separate problems because of the absolute value. So that's what that general tip was about. And since the two one-sided limits exist, the two-sided limit is equal to this number as well. Thanks for watching.